One of the greatest mysteries of human action is the mystery of whether we do the things we do that ultimately shape the kind of life we have and lead is a matter of our own volition and action and choices, or whether it's very much pre-ordained in some way and a consequence of our legacy or heritage or the actions of other supernatural agents. And I mentioned in the title of this talk, the Stardust, that we are, all of the large-scale world that's made up of things beyond hydrogen and helium, is the result of supernovas of stars which built up all the heavy elements. So there's a certain sense in which everything in this large, grand metaphor comes from the stardust, from the dust of stars. But it's also true that in this whole issue of what animates us, what motivates us and moves us, there's been historically a strong sense of the out there, the stars, having a very big role in it. And the various kinds of identities given to the constellations and the cycle of the seasons, the names of the constellations, and this is Aquarius, the water bearer, you see Capricorn. These ideas are very strong that there's something about the stars that obviously governs the seasons, so maybe it also governs the way human beings behave. And so that's one of the strong themes that offers an explanation for this mystery that we constantly face, that it's in the stars. There's an external force of stars and perhaps gods in the stars that are the source of the animation and activity of humans. Now, probably the person or in mythology who is the most notable representative of this thinking is Oedipus in the myth that is one of the oldest myths in Western civilization. It's the story of a king who has a son with he's the king of Thebes. His name is Laius, and he's married to Jocasta. And they have a son, and the oracle tells Laius that this son is destined to murder him and marry his wife, marry his mother. Well, this is something he doesn't want to have happen, so he binds this child up and has a shepherd take him off to expose him and kill him, and so he'll be destroyed. But as in all these kinds of stories, the shepherd doesn't do the job, and instead he sends him off to another king in Corinth named Polybus, who raises Oedipus. And in the course of this growing up, he hears rumors that he is not really the child of Polybus. And the oracle appears, and he consults it, and it says, no, you're destined to kill your father and mother. But he still believes he is the child of Polybus, and so he flees. And in the course of his journey back to Thebes, where he originally came from, although he doesn't know that, he comes to a crossroad and encounters a very vigorous man in a chariot ordering him out of his way, and Oedipus is not going to take that from this man, and they get into a fight and he kills him. And of course that is his father. And he then proceeds to Thebes, where he's welcomed, but there's a terrible plague that's going on, and there's the Sphinx has cursed the city with a plague, and unless somebody can answer the Sphinx's riddle, the city will lay under the plague. And Oedipus says, what's the riddle? And he's given the riddle, and he solves it, and the city is spared. And so he is the hero of saving the city. And by the way, we have a widowed queen who needs a very strong leader to be her consort or to be her husband. And so he becomes the queen's new husband. And when he discovers what he's done, which he does, he puts out his eyes. And this is a wonderful ceramic mask of Oedipus. And this is a painting of Oedipus leaving the city of Thebes in disgrace after it's been discovered. He's being escorted by Antigone, his daughter. And you can see he's blind, and the people are all horrified at him. So that's one of the strains, and it's accompanied by myths in other cultures as well that present a strong portrait of something beyond us that makes us what we are. It's not the here and now, it's something outside us. And one of the strong notions of that in Eastern philosophy is karma, that people have karma. But if you actually look at karma, at least in the Buddhist tradition, there's a strong way in which karma is part of the cycle of rebirth. It's part of the cycle of reincarnation. And so the karma actually has a history of living at another time. So there's a way in which people do create their destiny in those philosophies. It's just that they don't do it in this life. They did it in a previous life. And if you want to fix things up for the next life, you better do something right in this life. So there's a way in which the reality that we experience, that we're not totally the creature of some external force, makes its way into these philosophies. Now, the other tradition that's very important, especially in Christian cultures, is the issue of that people definitely are quite free. In fact, God created them with absolute free will. But they are tempted and they are acted upon by other demons or gods, the devil, who tries to get them to do the wrong thing. And the job of the Christian soul is to do the right thing. So temptation is a big issue. We are tempted to do the wrong thing, and we're free to give in to the temptation if we want. So one of the great kind of icons of temptation is the 4th century hermit and monk Saint Anthony. And in this painting, which is from the early 20th century, here is Saint Anthony beset by one of the great temptations that always comes into the picture, the whole issue of behavior and free will with respect to sex and men and women. And here is poor old St. Anthony completely under assault with temptation. This is another painting by Max Ernst, which I think is a little more realistic to what's going on here. I don't know if you can try to... This is St. Anthony. He's lying on his back. This is his head. He is totally being attacked by these creatures who are the creatures of temptation, and they are at him everywhere, just like in the previous slide, only these are much more generalized, and I think they speak to the way in which we are subject to petty temptations, to be short with somebody, to hurt somebody's feelings, and also the petty temptation to retaliate, unnecessarily maybe. or the petty temptation to eat way more than we should have of that chocolate cake, and on it goes. So there's just a whole range, a kind of constellation of give and take, struggle that goes on, that is captured by the notion of temptation. Finally, I want to mention another figure in literature that I think brings us into a much more realistic presence of the issues that we are talking about in leading a human life and in facing how we will, what we want, what we do. And that's Anna Karenina. This is another late 19th century painting, the heroine of the Tolstoy novel. And Anna Karenina, I want to mention one, I think most of you probably know the story, but I want to mention that she is married to a Russian bureaucrat. She's from a high strata of society in Russia of the 19th century, and she has a son. It's a very kind of stale marriage. He's a very kind of stuffy guy, and she is a very vivacious and lively woman. And one of the Tsar's hussars in the guards, who's a very great horseman, catches her eye, and he catches hers, and she falls into a love affair with Count Vronsky.
Is that Anna Karenina?
Anna Karenina.
Mm-hmm.
And the story takes off pretty much from there. It's a very rich and wide-ranging story involving lots of family behaviors, not just this pair. Beautiful, rich story, much more realistic to what life is actually like. And Anna is a kind of tragic figure who eventually will end because she's going to lose her son. She is going to bear a child with Vronsky. It is going to be a very difficult and hard life, and she eventually is going to throw herself under the wheels of a train. But what I want to point out is when you read this novel, you see how Tolstoy, I'm told, Anna tells me that, he wrote that. He was quite the moralist, and he wrote Anna because he wanted to show the evils of what happens when you don't follow the tried and true and the right course in marriage. And the truth is, when you read the book, and I don't know if Tolstoy himself confessed to this in his journals, perhaps he did, that he fell in love with her. He could not condemn her or judge her in any kind of simplistic way. And there's a way in which the story defies a certain kind of moralization. And I think that's much more realistic to the situations in which human beings find themselves. And I think it's much more realistic to our situations as 20th century human beings, because it is very unlikely that any of us is going to murder our father and marry our mother. But probably most of us have faced the issue of whether or not to break up a marriage. So now, the dimension that I want to particularly focus in on in the first half of this talk is another way of looking at what's going on here. We looked at sort of the karma ruled by gods and fate, and then we looked at the free will in the presence of demons and temptation. There's another dimension, which is what's actually going on in the human brain, mind, and emotional system when we will. What is going on? How is it played out? And I'm going to introduce that, again, going to literature, to the novelist Flannery O'Connor, who I think got it very right when she said, "We are not one will, but many wills conflicting together." And I think that's what the neurology and psychology of the human brain and emotional system are going to tell us. We are made of many, many wills within. and they are interacting. There is a community within our brains and minds. It's not one thing. So we're going to have to look at the brain, because that's where the emotional system is focused. But it's always a mistake to think that the brain is all about where the will is and where the emotional system is. It is really a complete emotional system spread throughout the entire body, but it is focused and concentrated in the brain. So the first thing I wanted to point out is the human brain, compared to the chimpanzee brain, which is one of our closest primate relatives that we're only about 10 to 15 million years away from. And this is the modern human brain, which acquired this size roughly about 200,000 years ago. So we are not the same creature that we were 200,000 years ago, but in terms of brain size, but maybe not necessarily organization or function, but in terms of total amount of capacity, we're about the same. And it's enormously greater than the chimpanzee. And I just want you to look at one aspect, which is this great big frontal lobe here. The chimpanzee has this ridge, but there's no brain in that ridge. The brain is back here. It doesn't have this prefrontal cortex, that's this area here, this big prefrontal cortex that human beings have. And there's something enormously social about that prefrontal cortex, and also something very much related to the kinds of give and take and interactions that come into most of our free will situations, which all have to do, for the most part, with how we interact with other human beings. So here is, we open up the brain and we look at it, and when you look at it just from the outside without any ability to see into the microscopic aspects of it, it looks like a bowl of pudding, but it's not. And when we open it up and look at it from a nervous system point of view, we see that it is rich in nerves and nuclei where the nerves join and synapses where the nerves connect and fire off with other nerves. The brain is full of electricity, which is what your computer is full of, electricity, because both of them do computation, and the brain does computation using electrical circuits as nerves. But not only, the brain also does computation. In fact, the whole body does computation using fluids, using chemical circuits, chemicals that go into the bloodstream and are sent to other parts of the body, and they pick up the signal and they respond and computationally respond to it. So there's both a chemical network and an electrical network. So I think 20 years ago even, most people would not accept that the things that we do that are most precious to us involving the human mind and the brain, well, people would say, well, of course we have a brain, yes, but that's not the mind. The mind is not in the brain. The mind is outside me someplace. But I think what the modern neuroanatomy of the brain shows us is that we have a nervous system of 100 billion neurons and 100 trillion synapses. Those are those junctions. The modern central processing unit of your computer is 2 billion compared to 100 trillion. So you're understanding what I'm saying right now. You're hearing my words coming through the air as sound waves. They're going into your ears. They're activating the receptors in your eardrum. It's activating a signal that goes through the audio nerve, goes into your brain. You're processing what I'm saying on the fly, and it's going into your brain and mind, and your memory is remembering some of it. You're going to forget a lot of it because it's a little too much to remember, but maybe you're going to remember this part. It is absolutely amazing. It takes tremendous power to do that. And there is something for those 100 trillion synapses to do. So this is a typical cross-section looking at the brain. I just wanted you to see what the nerve cells look like. And this is what a synapse looks like. It's a on-off switch. So here's a nerve that's sending out. Nerve has two kinds of ends. It has these ends called dendrites, which are like little nerves going out, wanting to hear some signals, wanting to get some messages. And then it's got a major nerve that comes out that is the axon, which when it receives all of these inputs, the voltages adjust inside that neural body so that finally the synapse fires when it gets enough signals that lift that up. And so the switch is closed or open, either way, change of state. And that's the fundamentals of computation, is to have something that can either be on or off. And what the organization of all of this information will be is a whole constellation of on and off switches. Now, I hope that doesn't sound too kind of crude, but there is a certain sense in which the fundamental element of any kind of thing, and it's part of nature itself, which is to be this or to be that, to be on or to be off, to be at a high voltage or be at a low voltage. If you can do that, you can compute. Now, what this is a little bit of these, looking at these nerves that are in this system that we're going to take a strong look at, the cortico-limbic system. And you see that it's got lots of nerves heading in all sorts of directions. And this is it. Now, don't worry about all these names, and don't let all of... I want you to just focus in on a couple of things. First of all, look at these blue areas here. These two big blue areas. This is up in that cortex, that prefrontal cortex. This area is very important, and it's very human. Right below it is another part of this cortex called the anterior cingulate, ACC. So there are probably at least 24 structures and organs that are probably pretty crucial for all these things. It's too many people on stage. I'm only going to bring on stage about 4 key players. But they carry quite a bit of weight. And if we can watch these players play, we can learn a lot about how our emotional system has evolved, how it's come to have the form that it has. So that's these two guys. The PFC, the prefrontal cortex, is one of the big players. The other one is the ACC, this anterior cingulate. And then down here we have the amygdala, this little guy. This little guy is a big deal. The little guy is, if you want to visualize it, you can, this is a nice way to look at the brain actually. You can bring your hands together and with your fingertips and then put your thumbs, just dip them in there. This is a pretty good model of the human brain, looking at it from the base of the spinal cord. And out here is the prefrontal cortex, and the amygdala, we should really say amygdalae, there are 2 of them, they are like your thumbs. So they're about the size of olives, but they have a very big role to play. They are the center of most of the fast-acting emotions, fear, and so on. Now, finally, I want to bring on stage the hippocampus, because it's got a lot to do with learning and memory. And the last guy I want to mention is the hypothalamus. We're not going to really talk too much about him because he's kind of an agent, in a way, for the amygdala and all these other structures. But it's the hypothalamus that connects with the chemistry, that's going to connect with the adrenal gland that will fire off these chemicals into your bloodstream, like epinephrine or any of these chemicals that when you're frightened, adrenaline will become pouring out. The hypothalamus is this link between computation and nerves, which in themselves don't do anything, and bodily action. Start running because here comes the adrenaline from the hypothalamus. So it got the signal that was an electrical signal from the amygdala, perhaps, and then it changed it into a chemical signal, which then goes into the bloodstream and gets you moving, or gets you to stop moving. So let's talk about these actors a little bit individually. So here's the first guy, the amygdala. It's a very emotional, it's like the hothead of the brain. And I'm going to be rather crude about this because it's a very kind of filigreed story, but just to a first approximation, it's the hothead. It's kind of effortless. You don't have to work hard to make your amygdala work. It does it. You don't have to work hard. Easy. And it's very much a part of fight or flight. It's got a very fast response time. It can act very quickly. And it's also a legacy program. By that I mean we're not the only mammals that have amygdala or cortex or prefrontal cortex even. But this is one of the oldest parts of the human brain, the amygdala. Okay. And here it is. The amygdala is one synapse away from that hypothalamus, which is where the hormone release is and the action causes action. And most of the other players that we're going to have on stage here are more than one synapse away. They may be 2 to 7 synapses away. And you can see the more synapses away you are, it's like you're trying to send a signal on a party line. And there are other people, other organs trying to send signals on the party line. And there's a way in which the hypothalamus is, since it's the source of action, there's a way in which that's a kind of destination that they all are looking for. Because if you don't have the hypothalamus, there's not going to be any action, and there's no point in having emotions unless there's action. Emotions are the things that put us into action. Okay, now the prefrontal cortex. It's a kind of real contrast to the amygdala because it does a certain amount of reasoning. It's also difficult. The amygdala is effortless. What it does is effortless. But the prefrontal cortex it makes demands. It forces you to think. And it has many, many synapses. It's a recent complex network. And it's not fast. It's slow. On the other hand, it's very valuable because there are times when you can't just jump up and run because you got frightened. You have to... You could jump up and run off a cliff. But if you can think about it a little bit, you say, no, I can't do that. I've got to rethink this. So there's a way in which the prefrontal cortex is a counterbalance to the amygdala. And finally, the hippocampus here is a source of emotional memory, where we remember things, where we maybe burned our hands. The hippocampus is a good place where these emotionally laden memories, and they may be things about hurt feelings and a love affair. Those kinds of memories also have some place in the hippocampus. I want to emphasize the prefrontal cortex again. It's larger in humans than in any other primate. It's late to evolve. The volume, the size of, if we look at orangutans, gorillas, chimpanzees, human beings, the size of that prefrontal cortex scales with how big the social group is. So orangutans, even though they're primates that are closely related to us, they are very solitary. they have a smaller, proportionally smaller prefrontal cortex. Chimpanzees, it's pretty big because they're very social. They live in groups of about 30 to 50. And the volume seems to scale with the social group. And what that tells you is the prefrontal cortex has a lot to do with social interaction. You've got to remember who all your mates are. Who did you a good favor? Who you got to be careful of because they're dangerous, and so on. And it's late to mature. Our prefrontal cortex isn't fully formed until we're in our early 20s. So you've often heard that teenagers have an inadequate brain to moderate their behavior. And this is the truth behind it. They have not learned. On the other hand, that prefrontal cortex, as we're going to see, can't be fully developed until it knows what the situation is. It has to have experience. Just like a baby's visual system will not develop unless it uses its eyes. Now, that ACC, that anterior cingulate, that is like the judge. So if the amygdala is the hot-headed emotional guy, and the prefrontal cortex is saying, no, 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 think about it, you've got to think about it, don't just do it, and the amygdala is saying, act, 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 got to do now, got to do now, no, 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 think about it, think about it. The ACC seems to play some role. That was that little blue thing underneath the prefrontal cortex, seems to have a role in mediating these. And don't we find that we have kind of hotheads in society? We have people who want to think the problem out forever and ever. And then we have some people who are sort of like the judge, the moderator. It says, okay, that's it. So that's everybody on stage now. That's the human emotional system. And we'll now say something about where it came from. Yeah, I guess I want to just emphasize again that the prefrontal and the ACC sort of are on this really thoughtful aspect of the brain and emotional system. And the amygdala, hypothalamus, they are sort of leading representatives of the strongly emotional part. And I think this is a beautiful way in which thought, deliberation, reasoning is present in the brain, and emotion, raw emotion, is present in the brain. And we know that these two things are constantly going back and forth with each other. So, where did this come from? Well, the first thing it comes from is genes. The formation of our cortical limbic system, this whole brain emotion system, nervous emotion system, is got a genetic origin, which means it also came from natural selection through many hundreds of million years of animal evolution, and finally the last maybe million years or so of human evolution, which shaped and changed and modified. The other thing is it's designed to learn. Nature knows is a kind of euphemistic way of putting it, but you can't hardwire everything, because the nature of evolution and evolutionary life is it's not the same. It is constantly changing. It's moving and it's rolling. So it's not surprising that there's an evolutionary response, which is to design genetic structures which are going to be inherited from the generation that went before, and you're stuck with it. But it's got a certain plasticity, a certain capability of changing its shape, of making itself grow in response to the environment in which it finds itself. And that's true with the development of babies. That's why The baby's brain is got a lot of development that has to go on after it's born. New connections are formed, old connections are chopped off. And as you go through emotional life, where you have to be part of the society as a young person, you have to deal with this complex interaction with others. And the prefrontal cortex has to learn how to do that. Oh, finally, actually, there's also invention. That is, each new situation has a certain amount of rewiring that can take place. There's not a whole lot of rewiring that can be done to the brain, but there is some amount. And so invention can make its way into the brain if it's always in the presence of this same social situation. Pretty soon, it's going to learn it, and it's going to incorporate it through that first 20 years of learning. So here's a picture at the molecular level. If you don't have to completely understand it, what I'm trying to show you is here we start with molecules of DNA. These are things that are the dust of stars as well. These molecules are regulatory molecules that regulate the genes that code for our building our bodies and also regulating our behavior. So then this thing is a blow-up of this thing, which is then sitting inside a whole strand of DNA. So this is one particular gene. And it controls how the nerves are going to actually get laid out in the various structures of the body. These regulatory elements, there are molecules. So, at birth, we have, I've euphemistically put little dials here. And you can think of them as settings. Because we know that in the varieties of the way of different human beings have different, and different animals as well, have different settings on all these fundamental issues, like fear. Some people's little dial is turned way up to be really, they're slightly fearful, more fearful than average perhaps. Other people, dials turned to where they can tolerate a certain amount of alarm. Other people, dials may be dialed towards a little more tendency to sadness, a little more tendency to happiness. And there's a whole lot of these dials, a whole lot of these genes. And we're all a collection of different settings. We're set slightly different ways. So the network comes in with an initial setting. And then it's going to develop with age and change. So these dials that we're saying initially, as we gain experience as babies and as small children and even as young adults, and even on through into adulthood, we are experiencing the environment and tuning up these settings so that life experience is actually changing some of these settings of the neural system in the brain. So learning is a very big deal, and that prefrontal cortex that doesn't get fully developed until the early 20s is one of the big learning components. It's not the only one, but it's probably the most important in the cortico-limbic system. And then also there's a possibility for invention and novelty. It's always small, but it does exist. And we need it because what's coming tomorrow is not going to be what we're facing today. And what we face today is not what our ancestors faced even a generation ago. Maybe we're being tested on that right now, just in the whole business of governance. So, will is a community of these actor agents in the cortico-limbic brain. I mentioned these 4 or 5 key players. And they are, in a way, a small version of a parliament. or a Congress, pushing and shoving against each other, trying to get their way, but not being able to get it. And ultimately, maybe thanks to operations like that of the anterior cingulate, some kind of judgment, some kind of resolution happens, because we have to act. We can't stop. You can't just go into a comatose state. You have to act, even if you don't have perfect information. Time doesn't stop. The roll of motion of life is always moving. And so we see that there's a community of wills in these various brain structures. Some are fast and pre-programmed, some are slow and thoughtful, and some resolve conflicts. Kind of neat. And the development of the will starts with a genetic initial condition, and then the emotional brain develops and learns from its environment for the first 20 years. That's pretty neat also. And finally, I'm not going to say much about this, although at this point in terms of neural networks and such, but it's going to play a role in what I'm going to discuss in the illustrations I want to give. We are very much connected to other brains and minds. There's a way in which the whole society, it's a little crude and simple-minded to say that there's a mind, there's a social mind, but it has some truth in it. And what we think and do is shaped by the social community. We're biased in many ways by the social community. So, back to Flannery O'Connor, we are not one will, but many wills conflicting together. And now I'd like to say something about all of this in action in real life situations that we have to deal with. And I'm going to talk about tragic situations, the tragedy, what I call the tragedy of the emotional brain. I don't mean to be talking about tragedy exclusively, but these are also human situations that are very timely, that are present and we face and have to kind of try to come to terms with and make sense of, and perhaps what we have learned will help us get a little better grip on what's going on here. So I'm going to discuss 4 human beings whose history has covered the last 40 years, and or actually a little bit more, and illustrate some aspects of what the emotional brain and the will might be doing. The first one here is Charles Whitman. Charles Whitman was a honorably discharged Marine in the 1960s. He served well, and he had a military scholarship, and he was studying engineering at the University of Texas. And in 1964, I believe, is when this happened, he began feeling slightly uneasy and troubled by several things. Some of his friends said he started acting a little oddly, but he became very sensitive to what people might be doing or thinking about him, and he particularly was kind of uneasy with his mother and his wife. And one morning he put on all of his military fatigues, and like so many men, he also had a collection of guns, and he took his guns with him. And he first of all went to his mother's home and murdered her in her bed. He then went to his apartment and murdered his wife, and then he got the rest of his arsenal and proceeded to the University of Texas campus and climbed up the bell tower, whereupon he began firing randomly at people that came by, finally killing almost 10 to 20 people before he was shot. Now, we've heard this over and over again. We've heard this many times. We've seen this many times. What is going on here? Well, Charles Whitman, fortunately, has, I think, a rather somewhat simple explanation of what is going on here. Charles Whitman was autopsied, and his brain was dissected, and a cancer tumor was found on his amygdala. Now, it's not surprising then that there's a malfunction going on here, an amygdala malfunction. But something that you can miss if you say, well, that's it, that's the explanation. He had cancer in his brain and it made him do this crazy thing. I want to point out that when people behave abnormally, they do so in very normal ways. There's a way in which what he was doing was perfectly normal. He's got his fatigues on, there's an enemy around, he's not sure who's the enemy. He thought this was his friend, but maybe it's his mother is actually his enemy. And what do you do when you have enemies? You get a bunch of guns together, and you go and you start shooting them before they can hurt you and do you in. Well, that's perfectly normal. That is socially supported by the society in which Charles Whitman. The only thing he's doing wrong, he's shooting the wrong people. But as far as getting a bunch of guns and shooting people goes, he has already learned how to do that. So it's not just simply that if we're looking for an understanding of how we can move away from these kinds of events, it's insufficient to stop at this and say, well, people who have cancer tumors, that's the whole story. There's a way in which, even though he had a cancer tumor, he was behaving completely normally, and if we don't like that kind of normal behavior, that's something we need to direct our attention to. The next tragic figure also is really tragic. I mean, a cancer tumor, what can we do about it? This is not quite bad at all. His name is Zhu Haiyang. He was responsible he was a Virginia Tech student, actually. And this occurred, I think, in 2007, maybe. He was a student from China, and he had become fond of another Chinese graduate student, a woman, and he had expressed his love for her, and she had rejected him. Now, he was so distraught. First of all, being rejected is a very emotionally challenging situation. Most people try to learn how to deal with it and get over it. But what if your dial is tuned up really high, especially for a man who stuck his neck out and said, I love you. And the woman says, I don't love you. Stop bothering me. This is enormously painful. And the pain was so great that he gathered up a butcher knife and went to one of the cafes and slit her throat in the cafe. Almost decapitated her, from what I understand. And immediately, he didn't kill himself, he didn't shoot himself, he just burst into tears and said, I don't know what I was doing. And he later just expressed the most enormous sorrow. He said, what I have done is going to be with me the rest of my life, which is of course true. But I don't think there's any doubt in the case of this young man that he was overtaken by a force more powerful than he could control. And this is not a cancer. I don't think there's been any autopsy done on him, but I don't think it's necessary. We can explain certain kinds of human behavior in the same way we can explain pole vaulters who can pole vault 17 to 18 feet because they have a body tuned up to do that and a natural endowment to do that. We have got to accept that there are some people that have genetic tunings that, in the absence of any correction or any moderating influences, any learning experiences to moderate them, can go off the edge. Can go off the edge. We know it just in terms of people who lose their temper. People who blow up. And they say, I'm sorry I blew up. I just couldn't help it. And there's a certain truth in that, but it's also true that there's a way in which if you have a very bad temper and it's destructive, steps can be taken to moderate it, to do something about it. So this is another slightly different illustration of how this corticolimbic system can work and produce results that we do not like. Now the third person here is, I think, the most puzzling, but I originally gave this talk at Lynchburg College, and all of my illustrations were men. And somebody remarked that the talk seemed very male-oriented. So I am including Amy Bishop. Now, Amy Bishop is a neuroscientist. She was Harvard educated, and she was a professor at the University of Alabama. And I have a lot of familiarity with having taught in a university, in a couple of universities, that the stress and kerfluffle of tenure is huge. I've seen perfectly reasonable, emotionally strong people become disoriented and upset and terribly distressed on the issue of tenure. Because Amy Bishop came up for tenure. I think you all know what tenure is. Tenure is that process whereby a professor who is doing his or her first teaching comes up to be reviewed, and if they have been successful and are well regarded by their colleagues, they are promoted to tenure, which in the old days was a lifetime position whose purpose was to allow you the political freedom to teach and to research whatever the spirit of inquiry wanted you to do without political influence. But it's gotten to be, to some extent, a kind of guarantee of a position. But it's still a very enormously difficult moment. And Amy Bishop was denied tenure by her colleagues. It's a little bit like saying, I don't love you. I don't want you to be with me. She was attending a faculty meeting shortly after the tenure denial came through. The faculty meeting had about 7 or 8 faculty members there. She was present and actively participating. And as the meeting was coming to a close, she took a gun from her handbag and shot 6 of them and killed them, and wounded a couple of others. She then went downstairs and called her husband up and asked her to come and pick her up. And when he arrived, the police had arrived by that time, and there was, of course, a huge collection of police and all around her. And she said, I don't know what you're talking about. That never happened. Now, Amy Bishop, I think, is the most puzzling of all of these cases. And I think she I don't understand exactly what was going on in her brain, and I think it would be really quite interesting for somebody to spend some time trying to think about that. It certainly makes sense when you're feeling stressed, when you feel, well, let me just mention one other thing here that's a very relevant factor. When you're part of a social group and you experience the embrace of the social group, your action and your behavior is going to be shaped by that. Let me give you an example of a different kind of study, but it bears on this. Studies were done where rats who live in rat colonies, they express their sociality and they know who they are by the scent. Each colony has its own special scent. And so they took a rat and removed it from the colony and in a way descented it. And then reintroduced the rat back into the colony. And the rat then became picked on and attacked. And to the rat, it was extremely confusing. Did not know what was happening. So there is a sense in which when you are rejected by a social group, there is a certain amount of social chemistry that, in a sense, has reversed itself. And not only said, you're not one of us, but we don't want you. I think that has to play a role in understanding the behavior of Amy Bishop, or anybody who is rejected from a group. Maybe for good reason. Maybe they're just incredibly difficult people and they create a lot of hostility. But that leads to a loss of the social moderation that most of us normally experience. And when that's gone, there's a certain inhibitory behavior that is lost. I don't mean to say that that's the whole explanation of Amy Bishop. There's something else that I should mention. After this murder, it was pointed out that she had accidentally murdered her brother some 20 years before. And what was said by her mother and herself was an accident. She was handling her father's shotgun and it accidentally went off. So this was then reinvestigated, and there were lots of puzzling things that didn't add up about that. For one thing, the police investigation, her mother was very close friends of the head of the board of aldermen or the board of governors of the town, and she had managed, somehow, the police managed to lose the file after they had declared it was an accident. Well, an investigation was performed, a thorough investigation, and there were many things that just didn't add up. For example, they found finally a police report that the gun had been reloaded, had been a new shell had been put into the chamber, which is not something you would do instantly if you would accidentally shot. At least it didn't seem like that would be the case. So this is still a very puzzling case, and Amy Bishop is still alive. She is in the faculty member families who she had shot had collectively made a request to the court that she not be given the death penalty, that enough killing had already taken place. And it was respected, and she was not sentenced to death. She was sentenced to life imprisonment. Now, the last person I'm going to talk about is Nidal Hasan. Nidal Hasan was born in the 1980s. No, a little before that. In 1988, he graduated from high school and he entered the army. And he began studying for officers' corps, and his college education was covered by the Army because he was signing up for basically a life career. And after finishing college, he went on to medical school and entered medical school and became a psychiatrist. He was born of Palestinian immigrant parents, but he was born in America. And it was his fate to have finished medical school and sort of begun his career about 2 years before 9/11. Now, you can imagine that there might be some difficulty with a Muslim in the army, but after 9/11, you can imagine that it was going to be really quite traumatic. So he's bright-eyed, he's hopeful of a career, and something happens that's out of his control, and suddenly he is feeling it. Now, he is going to work his way along to dealing with this problem by becoming more and more isolated and feeling more and more wronged, that he becomes the Fort Hood shooter, who goes into Fort Hood. I forget the exact date, it was several years ago now, but he just had his trial this past year. And he started shooting and killed several, I think it's on the scale of more than 10, and wounded several people. And he himself was wounded in the shootout. And this is his more recent picture. Now, I think he explained his behavior by saying he had come to see that the United States was actually his enemy because it was attacking and destroying Muslims and Muslim culture. And people can argue about whether that's really the case or whether they are or aren't. But we know from the emotional system is in a certain way simple-minded. It's not really tuned up to make really fine, careful distinctions because it needs that prefrontal cortex to help it do that. So there's a way in which the animosity, well, you can still see the animosity against Muslims pop out. It just popped out on the mall when all of these people came and started calling the president a Muslim and that he should come out, should get off his knees and come out and apologize to the American people. So this is still an emotionally laden substance that is flowing around in the body politic. And people experience it, and people experience the rejection. But Nidal Hasan, after 9/11, is a little bit like, I don't mean to compare him to a rat at all, but he's a little bit like an animal that has suddenly had its scent changed. And all the other animals now are responding to it differently. In trying to understand these cases, especially in the judicial system, we have traditionally followed what's called the McNaughton rule, which was Nidal Hasan insane? Was Amy Bishop insane? Was Zhu Haiyang insane at the time he committed the crime? Well, the rule has been, did they have the ability to tell right from wrong? And from the modern, and also that if they could, we expect to punish them. The judicial system has been moving along on that kind of coordinate system for the past 100 or 200 years or more. So neuroscience tells us there's more to this, that there has to be some kind of ability to control harmful emotions. That is much more the point. And I can see a lot of people saying, well, you can't believe them. They say, I couldn't control myself. Well, we don't want to hear it. And it's true that people can abuse their behavior. They can excuse themselves from things that perhaps we shouldn't excuse them for. But it's on much more solid neuroscience ground than the McNaughton rule. And it seems that rather than punishment, we ought to be talking as a society about how do we control harmful persons, harmful to themselves, harmful to others, not how do we punish them. We are not one will, but many wills conflicting together. So that is the end of part 1. So in this part of the talk, we're going to step way back behind the stars, and we're going to talk about free will in elementary particles. Now that may seem like an impossible idea because elementary particles don't have brains or emotional systems. How can they have free will? It's clear that they do not have free will in the way animals or human beings might have. But in their executing their action, in going about their movements as elementary particles, they do have a degree of free will. In fact, quite a lot. It's not until they get into collectives of lots of particles that they start losing their individual free will. So, back to the stars, and the most elementary matter of all is the hydrogen and helium of the Big Bang. And from hydrogen and helium, we get protons and neutrons out of the Big Bang, and they make hydrogen and helium. And what I'm aiming to get at here are some of the simplest elementary particles, which are the hydrogen atom. But then, to make much more complicated life, we need all the rest of the elements, calcium, oxygen, and so on. And so we need to build that up. And 1 billion years later, the supernova processes the compression of gravity, forces all of these elementary helium and hydrogen atoms into fusion to make much more complicated atoms. And so we get all of these complex atoms, in particular the atoms of life, like hydrogen, carbon, nitrogen, and oxygen. Now, I would like to show you, or to explain to you, how atoms think. And when I say think, I'm going to mean compute, which is to have the capacity to take a certain situation and respond to it and produce a new situation. That's what computation is. And you do it with all of these on-off switches. So atoms are such simple creatures. They don't have brains and all, but they got two important properties. Well, they have actually more than that, but the two most fundamental that they have are their positions. Where is the atom? Doesn't have much else to talk about. And its momentum. Which direction is it moving? What is its motion? And so, how does it compute? Well, it uses the law of motion that nature has built into them. There's a law of motion that tells them how to compute. So, here's an atom thinking. And I'm representing it not as a quantum particle, but I'm representing it as a little marble, which you can do when all you're talking about is the large scale. It's only when the atom is interacting with another atom in a very tight space at very small velocities that we have quantum effects. So it has a position, it has a momentum, and it occurs at a certain time. And there are other atoms around. We've got positions and momenta. And the law of motion is a law that takes all of these atoms and their individual positions and momentum, or momenta, and from them it computes what their new positions and momenta should be. It's really one of the most beautiful and amazing things. Physics students do this, but we usually do it, physics students do it with only the really simple problems, because most what are called many-body problems, we've got lots of atoms here, are too complex to do by hand, but you can simulate them on a computer. And I remember the first time I did that, it was back in the 1960s. It was pretty basic computers then, but you could do some computing. And I remember making a little kind of just two-dimensional model of motion of particles bound by gravity, bound by their gravitational force. So each of these atoms or mass points was pulled by gravitational force. And it was stunning to watch it. It's like you throw these planets or mass points, mass particles, throw them in, and they, because of their gravitational attraction coupled with their movement, will organize themselves into a solar system. Now, this wasn't the solar system, but if you have the right energy levels, they will organize themselves into a series of bodies that revolve around one another. So that's what they do. So if you're here at this time, there's a law of motion that's going to tell you where each atom is going to be at the next time, and also what its momentum will be, what its velocity, its direction. The momentum is the becoming part. The position is the become. I am this position, but then my speed is related to the momentum, and that's the moving part. That's the part that's motion. And there's a law of motion that says, put in, I use mathematical symbols here, but Q and P are the usual symbols for position and momentum. Put in the position momentum, the law of motion will compute the new position and the new momentum. So this arrow is pointing in a different direction from that one. And this position is over here, it's not there. And I thought I'd open up the box, like we opened up the brain. And this is what the law of motion actually, this is the mathematical form of the law of motion. It involves this very important function of the positions and the momentum, which is the energy function. So you've heard that energy is very important, and energy is the big organizing deal in the motion of particles. Energy is it. And energy is what also contains the law. The law of motion is framed in terms of energy. Okay. And these are atoms that are thinking classically. They're thinking like billiard balls, the way billiard balls would think, or planets going around the sun. They're really not atoms at all at this point. But we're going to see how they can become atoms in the quantum region. So the other things that atoms do is not just move and collide with each other. They form molecules when they collide. And so we have the building up of molecules in which these protons, the proton is the hydrogen atom without its electron. So hydrogen and protons, they're essentially the same thing, except for just add the electron to it. So I'm showing an important molecule here. Obviously kind of complicated, you can see that, but don't get led astray by it only contains these four atoms: hydrogen, carbon, nitrogen, and oxygen. And these are nucleotides of DNA. So I picked a really important molecule. And this is one, I just wanted you to understand how real these atoms are, because these are a bunch of carbon atoms. This photograph is actually a photograph of the atoms taken with an electron microscope. So atoms are real. Those carbon rings that you saw are real. So molecules think what their new positions of momentum should be, but they also think what new molecules they should form with other molecules. You know, the classic example you have is H2 plus O, it gives you H2O. Well, obviously with some different stoichiometric coefficients. But. So what I want to just point out is, especially these molecules that involve carbon in these carbon rings, they can think logically. This is a molecule thinking logically. Now, I won't tell you what the name of this molecule is. It's probably got a rather complicated name. But there's one additional player here besides the carbon and the nitrogen and the oxygen and the hydrogen. It's sodium. That's the atom that's in table salt, sodium chloride. Now, how does this molecule... Now, the molecule is this whole big molecule here. Pull the sodium out and take this hydrogen over here out, or put them in. What this molecule does is it's able to compute what you would compute if you were saying, if I have to go out to the store and it's raining, I will go into the closet and get my umbrella. So it depends on two things. It depends on, I have to go to the store and it's raining. Now, if you don't have to go to the store, there's no need to go to the closet and get your umbrella. And if it's not raining, but you do have to go to the store, there's still no need to go get your umbrella. And if it's neither raining, nor do you have to go to the store, you also don't have to go to get your umbrella. This molecule is doing that. What you would do in your mind for that, this molecule is doing. And I won't go into the details of how it works, but what happens is when you put a hydrogen proton into this molecule, it changes its structure, but it doesn't do anything special. And if you don't do the hydrogen, but you put a sodium in here, it will also change its structure, but not in any significant way. But if you put the hydrogen here, and you put the sodium here, it gets into action and starts emitting purple light. So you see how this is a little computer. It's computing the umbrella rain problem. That problem is called, it's a conditional logical function. If is a conditional, and is a connective, a logical connective that says there are two things involved. And there's a molecule that does it. This molecule performs 13 different logical operations. I don't even know what they all are, and I'm not going to tell you about them. I just want to tell you how, what an exciting period in chemistry the present is in terms of the computational structure that's just in the nature of being a molecule or an atom. Now I want to step up. I'm going to step up to trillions and trillions of molecules of lots of different kinds, but still a very small thing, a biological cell. This happens to be an E. coli cell, the kind of cell that's in your gut. And what I want to persuade you about is that cells think. And how do they do it? They do it chemically. They do it with chemical reactions that change the states of the biomolecules that are inside them and on their surfaces, changes those molecules in response to what the environment might be doing and what's going on inside the cell. There's a way in which the cell's computer, because the surface, these cells do not have brains. They don't have even the reproduction system of more complex animal cells. They're really very simple. And so there's a way in which all the computing, or most of the important mind, if you want to think of it, of the cell's mind, is in the cell's surface, because that's where it's getting input from the outside and then making chemical changes in response to it the thinking, and then maybe sending in instructions to the other structures inside the cell to make a little more beta-galactose or something to digest the enzyme that I just detected is out there. So the brain of the cell there's a good argument that can be made. It's mainly concentrated in the surface of the cell membrane. And here is the cell thinking. This is, again, E. coli. And this is sugar. So there's a sugar solution here, and where you see heavy dots, there's a lot of sugar, and where you hardly see any dots, there's no sugar. And so here, between here and here, there is a gradient of sugar, which means there's more sugar here than there is here, and the cell runs. It has these little flagellae, and it wiggles its way into the high concentration because it's designed, that's what it's for. It does metabolism. And if it finds that it gets itself into a low concentration, it can't detect any gradients, it doesn't waste its energy swimming around. It just kind of tumbles. It's just waiting to pick up a sugar gradient. And when it picks it up, it's going to go to it. So, the biological cell, which is made of trillions of atoms, also thinks. And so they have minds and wills capable of executing simple actions of life. In this case, go to the sugar. Now that's not going to allow you to add 2 and 2 together or discriminate whether somebody is hurting your feelings or not hurting your feelings, but it does for what life for an E. coli bacterium is, it is in fact to metabolize. So this is vastly insufficient computational capacity for complex behavior, including consciousness. But it's on a continuum. The ability to think is part of the universe. It's part of the structure of the way matter is put together. Now, of course, we were just there where we saw that nerve cells are very important, and nerve cells think with those synaptic junctions that turn off and on as logical switches. And animals think with neural networks of billions of nerve cells focused in the brain. So thinking, computation takes place at all levels of matter, starting from atoms, and even subatomic particles also think in this simple way, this computational way. Simple molecules, macromolecules like DNA and proteins, then up to cells, organs, animals, societies. There is a continuum of thought. Now, I want to conclude by telling you about quantum thinking, because it has very much to do with freedom. And I'm going to use our DNA as an illustration. So these, let's see here. So I'm going to use DNA molecules. And DNA, go on here. So DNA is made of 4 central nucleotides, 4 different molecules, and only these 4. And they are strung together like beads. They're actually bonded on a backbone of another set of molecules that includes phosphorus. But just the nucleotides themselves that name the letters are just our good old friends here, hydrogen, carbon, nitrogen, and oxygen. And they are like the letters of an alphabet, and they encode these instructions that make bodies, brains, and behavior. So, go back here. So, the particular names of these nucleotides are thymine, adenine, cytosine, and guanine. And we're just going to call them T, A, C, and G. And that's how you distinguish the different letters of the code. Now, I think you all know that if you take a text, that's written according to a certain alphabet, according to a certain code, like the grammar of English, for example, and you just start to change it randomly, you are changing the text. And if this was the instruction set for how to bake a cake, you might not bake the same cake, especially if a 1 was changed to 100 on the flour. So small changes in the code can change what the code produces, what the code makes. So here we have these two sets of bases. So the letters pair with one another. They have this pairing aspect. So that T wants to pair with A, and C wants to pair with G. The other thing I want you to notice is that the cytosine and guanine combination is triple bonded, and the thymine-adenine combination is just double bonded. And it's got a proton, a hydrogen atom, that's sort of sitting out there. So they're not quite the same in terms of their bond structure, and that has consequences. So this one up here, it takes more energy to make these 3 bonds than it does to make these 2 bonds. And I've sort of represented energy like we might as if you had to expend energy in your car to go up a hill. You have to use energy to get up the hill and to get to a valley that's up higher than you are. So if you're down here, you have to pay energy to get up here. And if you don't have it, you don't get to go in the classical universe. Now, there is this hydrogen sitting here on this adenine nucleotide, and if this hydrogen could be moved to sort of be in this position, then you could flip the whole molecule and change the TA into CG. It would look something like this. So this goes down here, and that would mean jumping up the energy. Now, if this is a classical particle, it's a forbidden transition because the energy is insufficient to get there. There's an energy difference between the two. So if it's a classical particle, it's more like bouncing back and forth. That's all you can do. But if you're a quantum particle, you are not a little marble. You're not a particle, you're a wave. Now, in the quantum case, the wave is bouncing back and forth. In fact, if I could draw a little wave here, if this was a quantum particle, the wave would be bouncing back and forth. And as the particle got more and more classical, like a billiard ball, if I was to draw the wave, you would see hardly any wave here, and then it would jump up. Here's the wave, and then it quiets down. So the wave, as you go to the classical or large scale scene, the wave starts to condense and starts to look like a little marble. But here, in the DNA case, we are in the quantum regime. And so this quantum particle is a wave. Now that quantum wave, because it's not a particle, can penetrate this energy barrier. And it can go across and get to that other position. So this hydrogen atom can jump over here, and the whole molecule can reorient itself so that instead of TA, we now have CG. It's called quantum tunneling because you tunnel through the mountain. And quantum tunneling is one of the most important processes in chemistry and in life. The way not only DNA works, but also the way photosynthesis works involves some quantum tunneling. So the thing about quantum tunneling is you can go places that you can't go classically, but you can't go very frequently. There's a probability for this process to take place. It happens randomly, but the probability does depend on the energy gap. If you have a very big energy gap, the probability is very low. It can hardly happen maybe once in 100,000 times. But as these two levels come together, then the tunneling probability starts to go up. Tunneling rate goes up. Now, you can see that in the natural world, the chemical world, we don't want things to, if everything could tunnel easily, the chairs would be falling apart, we'd all be falling to pieces, there would be no stability. So it's important that these energy differences are sufficiently great, and nature just seems to come out that way, just the natural structure of hydrogen, oxygen, and nitrogen and carbon, when you put them together, they just manage to make this very nice energy difference, which is really the hydrogen atom that's a very big part of that, which is just right to tunnel every now and then, but not very often. And if this is DNA, if DNA was tunneling all the time, there'd be no stable code. You couldn't have life, because it would just be chaos in every reproduction. And if there was no tunneling, you might as well just have a copy machine, because there would be no mutation, there would be no variation and novelty, no natural selection to work on the new mutation. It would just be cold and lifeless, like a lifeless crystal. So DNA tunneling is a really important process. So DNA code changes spontaneously. The TA becomes CG, and now the code has changed. A mutation has taken place. So let's go back to classical mechanics that we were talking about when it was more like billiard balls. Classical mechanics is deterministic because it doesn't have quantum tunneling. Quantum mechanics reveals that there are unpredictable elements in motion, so that when you actually use the law of motion respecting the quantum nature of matter, what you get out here is, which I've tried to indicate by the new position in the momentum, you notice how they're fuzzy? They're almost what you might get if it was classical, but it's uncertain. There's an uncertainty about it. And if I redo it again, it might come out a little bit differently. And I do it again with the same initial condition. Every time it comes out just a tiny bit different. More or less the same, but just a little bit different. And that wiggle room is a secret of life. Or let's put it this way. It's a necessary foundation for life. So atoms do not think completely deterministically. Atoms think quantum. Much is determined by the past, but each new state has a quantum freedom in its computation. And quantum thinking is spontaneous, unpredictable, and therefore creative, or the basis of creativity when it's operated on by the environment, and small. Can't happen all the time. So spontaneous quantum transitions occur in living matter, and they are small. So the hierarchy of life complexity, spontaneity and creativity of nature originates in the unpredictable spontaneity of the quantum. And we will leave the stars where we began. Yes, Jim.
David, what you were talking about, the quantum tunneling, you said that was a recent theory, proposal, whatever.
Yeah, maybe.
But that quantum mechanics has been known since the 1920s and 30s.
No. That mutation in DNA is a quantum process.
Okay.
And that it is, in fact, a major source driver of evolution. That's still a somewhat controversial position.
And mechanism has been around for a
Yeah, I know. I agree. It's not surprising to me.
Yeah.
But some biologists who would say, well, when I was a child, I wondered about this. Oh, I wasn't a child. I was in college, actually. I wondered about this because the story you got
first of all, and it's still very much the story, right? Mutations are bad. Mutations are destructive. Be careful with X-rays. You might get a mutation. Watch out. You might get a cosmic ray come and hit your cell and make it and mutate. That is, change the DNA letters the way I was just talking about. Bad, bad, bad. But no. In fact, you've got to change those letters if you're going to have the dynamic of life. So mutations, spontaneous quantum-induced mutations, I think, is definitely. And it works out just about right because the probability is low. Remember, DNA has to be pretty stable. You can't, if the DNA just completely turned itself over every time, you couldn't make anything. So it's got to be fairly stable. That's its secret. Fairly stable, but not completely stable, so that then something happens. It's the great poetry of nature. Every great poet knows that the discipline of rhyme and rhythm is fundamental to making a great poem. But the genius is to break it just at that moment. And you create something beyond what you have. So, you're right, Jim. But given time, I think more people will come around to this.
I'm trying to figure my own mind. Are you saying if your DNA today is whatever it is, and then yours won't change, but descendant down the line and so forth? No,
yours will change.
Oh, you're saying these mine will change?
Yours is changing right now before your eyes.
Okay.
Well, not before your eyes. On average, we will generate about 100 mutations in our DNA.
But does that change it enough that we can identify me as doing something if I want to use my DNA?
We can still identify you pretty well if you only change 100 letters, unless it's one of the critical letters, like in a particular molecule called histone that manufactures histone. You change one of those and you pretty much derail the whole thing.
Well, what I'm getting at is,
it's like pulling the cornerstone out.
We use DNA as evidence now to release people from prison and all these other kind of things they weren't guilty of.
Oh, that's we're talking now about millions of letters. You know, this is on average a human being's DNA. Say between the time you're born and the time when you reproduce.
On down the line, though, say several generations or whoever.
Yes.
Their DNA may be completely different than mine today.
Be careful with the word completely.
Well,
but it will be different. It will be different.
Say it's 9% new. I still got 10% of mine or something.
Well, first of all, to be human. At least 99% of it's got to be the same. But to be you is not just DNA. Remember, the dials are set to start.
Right.
And then life experience is going to change those dials.
Correct.
So you are going to be a product of genetics to start with, but what is called environment, the changing and growing, is called epigenetics. That is also going to play a role. And where you are and how you, and previous life decisions that your parents made, that you made, the environment that you grew up in, all of these are going to have small impacts on the DNA that you're eventually going to pass on.
Some of those dials will stay in the same position down through the generations like that.
Yes, like that one I mentioned, like the histone complex, that's got to stay the same because it's so fundamental to all the cells.
That's the theory.
Yeah, and if you changed it, the cell dies before it reproduces.
That's just what I was trying to understand the connection. Because I was saying, you're locked in on, using DNA as a piece of evidence in a criminal case.
Sure.
And that's still going to be valid.
What I'm talking about here is at a much lower level. It's before you've got all the signatures of individuality and so on.
Do you give this lecture other places, or is this?
I gave it at Lynchburg College. This is the second time it's been given. But it will be up on the channel that Joe maintains and that has my lectures on it. So it will be available on YouTube.
Oh, okay.
Or actually, you can get it at my website. It's mirrored there.
Very good, thank you.
Any other questions? Yes?
You've got to project ahead and give us an idea of what kind of human manipulation can occur with the knowledge and expand the knowledge that we're doing.
Well, I think there's no doubt that we are at a transition period of human biology. And I think it's wide open. We don't know but that's the way it's been for all of life. It's always been wide open. So you have to have some confidence that there will be some wisdom along with some error and that it's not necessarily a recipe for bad things. Yes?
I have a question. Whether we're talking human DNA or earthworm DNA or whatever, does the sheer number of individuals affect the rate at which DNA mutates? Like if you had 10 earthworms and that's all there were 10 earthworms. Or you had 10 million earthworms. Would there be more likelihood that mutations...
It'll be different. It will be different.
But it wouldn't have anything to do with
It has to do with sheer numbers, yes.
It does.
Yes. I think the way to think about this is the difference between individual DNA production and, remember, you've got a society, you've got a whole collection of organisms, they're all mating with one another. There is sharing and mixing going on. That plays a very big role too. What if I just simply, actually Darwin was very fond of raising pigeons and breeding them. So those pigeon breeders, they would see a beak, and they had really good eyes for this. They would see a beak that was a little bit longer, and they wanted to make a long-beaked pigeon. They would breed that one. And think of the dogs, which are all descendants of the gray wolf. You've got these little mini dogs, and you've got these huge dogs, and that's all because you have selectively done this. You have exerted the hand of the breeder in here. Now, there's no hand of the breeder that anybody can detect in natural selection. You kind of wish there were such kind of...
Accept it or not accept it.
Excuse me?
You can accept that or not accept it, that there is no one there.
Well, what you...
There could be something that's doing it.
As far as people can tell, and they've done a lot of careful experiments about this, mutations seem to be random.
Yeah, I know. But that doesn't mean that it still can be done. You can randomly set up things that happen randomly.
Actually, you can't.
No, I basically disagree on that one.
No, it's actually a very fundamental principle of mathematics because the very great mathematician John von Neumann said, of course, those who think you can create random distributions with a mathematical process are in a state of sin. because it's actually deterministic. You actually have a rule. So here, it's like trying to make a code. People trying to make these codes that can't be broken, but of course, they were handmade. So random means really random. It's actually random is a very profound concept. We treat it very casually, but it's actually a very deep
That's
concept.
very important.
Get back to the lady that brought up a million earthworms.
Yes.
If you divide those a large number of earthworms into a lot of smaller subsets and put each subset into a slightly different environment, such as temperature, humidity, or whatever, over generations, would you start beginning to see differences?
Absolutely. We have some examples just in the nature of evolution. The evolution that's taken place in different continents. Madagascar, an island, very different kinds of species there, and because exactly that process was going on. It was going on naturally. Yes?
What's your stance on consciousness influencing biology and physics and quantum physics and such?
If you're interested in this, let me talk to you afterwards as well. I'm going to answer your question, but there's some important lectures that are on the internet that I would direct you to.
Yeah.
Very important advances in consciousness research.
Yeah,
Excuse me?
it's definitely it's like a new thing.
Well, it's been something that's puzzled people.
Yeah.
If you have enough computational resources, it's certainly possible, and in fact we do, we make computers that monitor other computers, that watch what other computers are doing, and computers that then watch what those are doing. So, if you have enough computation, consciousness does not seem to me all that mysterious. I think it's kind of wonderful, but of course, if I hit you on the head and make you unconscious, it goes away. So it's clearly a physical process. It's clearly deeply physical. It's not some kind of thing in the air. And I think it is basically rich complexity with a global reach that's overseeing all of these other little neural processes that are taking place in the brain and has a kind of global view of them and can dip down into them or dip out of them. It sounds very robotic, and it is kind of robotic, but I think that's, remember, 1,000 billion synapses. That's a lot of computing power, huge amount of computing power. And we're using it right now. I woke in the night not so long ago with just the slightest little itch on this eyebrow, and I just picked up my hand and just gave it a little stroke, at which point I woke myself up enough to be conscious. And I suddenly thought, my God, the thousands of neural circuits and trillions of molecules that were actively engaged in operating, and the cells that they made and the network that they had just for this simple little act. It was stunning.
When it comes out of nowhere, the intention to do it comes in this mechanisms to go through the process, but where it originates is the question.
I think that's where these competing, we just crudely boiled it down to these 4 players, but they're really more like a couple of dozen important players in the cortical limbic system. And the interaction of these players, I think, is a very helpful step in understanding about decision making, about how finally you intend. Finally you say, I'm going with that. Does that answer your question?
Yeah.
Yes.
When are you coming back for your next lecture?
In about a month.
Okay.
And it's slightly, what we're going to do for the rest of the year is a little in flux right now. you have any requests?
What's to be decided on the next step?
Well, last year we did a series called Wild Times, in which I tried to make some sense of this major transition that the human species is going through, and by default, the whole planet is going through because we are such an important part of the planet. This major time of change. It's a major time of change. If you're feeling a little upset and uneasy and confused, and it's perfectly appropriate. You should be. If you're not, there's something wrong with you. But I think you need to be hopeful also. We have gone through major transitions before as a species. We went through one bottleneck in which the population might have been reduced to only like 2,000 or 3,000 people. And it's hard to imagine that today, isn't it? In fact, we have the opposite problem. So we did Wild Times last year, with touching on several of the different aspects of that. And I don't know whether, I don't want to get too off into neurobiology, but I was thinking that what you need to do in the wild time is be able to think clearly. And so I was thinking of a series that had something to do with how to think clearly. So that's what I can tell you at this point. I could change my mind, though. Molecules change their mind. I could change my mind. Any last takes? Or okay. Thank you very much for coming.